Dear students, today we will discuss about a very important mathematical concept of operators. So what are operators? What are the different properties of operators? And what are some of the important type of operators? So this concept of operators will form a mathematical foundation for developing quantum chemistry. So the certain derivations that we would make in quantum chemistry requires us to understand this concept of operators. So first let us define what is an operator. Okay, so operator, it is a symbol. Okay, so operator is just a symbol for what? It is a symbol for a rule. So operator is just a symbol representing a rule. And what is that rule? It is a mathematical rule for transforming, that is for converting one mathematical function to another function. So an operator only represents a symbol for a rule for converting one mathematical function to another mathematical function. So these, okay, it is a symbol for a rule for transforming one form of mathematical function into another form of mathematical function. For example, you have this first derivative with respect to x d by dx. If I apply this, it only is a rule. Okay, if I write this symbol alone, d by dx, it does not carry any meaning. Okay, so I remember, an operator, if it is written alone, it does not carry any meaning. But if I write a number, or if I write a mathematical function in front of it, say for example sin x, I write a mathematical function in front of this operator. What does this operator immediately do? The operator will take the first derivative of sin x, that is cos x. So an operator here, therefore d by dx is an operator. Why? Because it converts one mathematical function, that is here sin x, into another mathematical function, that is cos x. So d by dx is an operator. Similarly, if I take d square by dx square, the second derivative with respect to x, it is also an operator. As I already told you, the property of an operator, if it is written alone, it does not carry any physical meaning. It cannot do anything. But once I write a number or a function in front of it, again I will write sin x. What it will immediately do? It will take the second derivative, okay, of sin x with respect to x. What is the result? The first derivative of sin x is cos x. If I take again another differentiation, it becomes minus sin x. So the second derivative of sin x is minus sin x. I will give one more example. Square root. It is also a symbol, okay, representing a rule. What is that rule? Until and unless I write anything beyond the square root, it does not carry any meaning. But if I write, for example, a number now, okay, if I write a number square root of 4, what it will do? It will convert this into, okay, another number or another function. In this case, square root of 4. Actually, there are two results, plus or minus 2. Okay, I will discuss about uh, those things later, where certain function gives two outcomes or two results. Here I will only consider one result, that is plus 2. So d by dx, d square by dx square, square root. All are examples for operators. These symbols are different and they carry their own meaning. Okay, the symbol d by dx represents a rule which is different from the rule represented by d square x by dx square. So this is the definition of operator. Now let us define what is an operand. Okay, operand is nothing but the mathematical function or the number on which the operator is applied. So for example, here I have applied this operator d by dx on sin x. Here also I have used sin x. So sin x is nothing but the operand. So operand is the function on which the operator operates. Okay, so operator operates on a certain mathematical function, and that mathematical function is nothing but called as operand. So in the above example, sin x is an operand. Sin x is an operand. For example, I will give one more example. Log, which is an operator, okay, of x square is equal to 2 into log x. So this x square is now converted into 2 log x after application of this operator. So in this case, log is operator, x square is operand, and this is the new mathematical function. So an operator is applied on the operand, yielding a new mathematical function. So in general, this can be written in a general form of mathematical equation, and that form is okay, A. So this represents an operator. So how do you represent an operator in general? By capital letter, okay, in most of the case A with a small cap. Okay, if in a particular equation you have to use more than one type of operator, okay, then we can represent one operator by A cap, the second operator by B cap. If there is third operator, you can use C cap. So generally operators are represented by capital letters with a cap. So A cap, an operator applied on a function f of x, which is an operand, gives a new function g of x. Okay, so g of x, this function is not given a special name. This function f of x is operand, but this function is not given any special name. So this is the operator, this is the operand, this is the new function, and this equation a of f of x is equal to g of x. Remember, okay, and carefully listen how I am reading it. It is read as a of f of x is equal to g of x. Don't read it as a into f of x is equal to g of x. And this general equation is nothing but called as operator equation. This equation is called as an operator equation. What do you mean by operator equation? Applying the operator on the operand, giving a new function, and writing down that equation is nothing but called as operator equation. So let us concentrate on this equation. Is this an operator equation? Yes, definitely yes. So if I compare this general equation with this particular example, so d by dx, which is operator A of sin x, that is the operator f of x, is equal to cos x, which is nothing but g of x. So this equation is an operator equation. The operator here is d by dx, the operand is sin x. If I take the second example, the operator changes, d square by dx square. Okay, now this is operator A, sin x, the operand f of x, okay, is equal to minus sin x. Okay, and minus sin x together, now I will take it as g of x. Okay, so this is also an operator equation with this operator A. So we will come across this type of mathematical equation very frequently in quantum chemistry, which we call as operator equation. Okay, now let us discuss about some important properties of operator. Before that, we will discuss about one important class of operator called as multiplication operator. So what do you mean by a multiplication operator? Okay, so let us take an operator. Okay, in the previous examples I had operators such as d by dx, d square by dx square. Okay, here the operator A is just represented by A dot. Okay, so you have an operator A represented by A dot, where A is some number, okay, or it may be a function, for example sin x or 4x square or x cube, so on. So it can be a number or it can be a simple mathematical function. So this dot suggests that I am multiplying an operand by this number or this function. I'll repeat, when I apply such operator on an operand, what does this operator do? This operator just simply multiplies that operand by this number or this function A. Such type of operator is called as multiplication operator. So just multiplying by A. And sometimes, okay, when we proceed further and further, we will sometimes forget to write this dot. Okay, we'll simply write A cap is equal to A. It also represents a mathematical operator. Okay, so multiplication operator when applied on an operand, that is f of x, it just multiplies the operand f of x by this factor A. A may be a number or a function itself. A may be even a function. Okay, by taking some examples, let us try to understand what exactly we are saying. Okay, examples. So this is a multiplication operator. What is this multiplication operator? Operator A is equal to 4. So what does it mean? When I apply this multiplication operator on a function f of x, it just simply multiplies that function by number 4. Say for example, the operand that I am using is x cube. Okay, now let us apply the operator on the operand. That is, let us write the operator equation. A of f of x. This is the left hand side LHS of operator equation. A of f of x. What is A in this particular example? 4, and I already told you it is a simple multiplication operator, so we are just multiplying it. Okay, 4. What is f of x? X cube. So this is nothing but 4x cube, which is a new function g of x. So this completes the operator equation. A of f of x, that is 4x cube, is equal to g of x. Let me take one more example. So this is a multiplication operator. So here, with what we are multiplying? We are multiplying a function by 4x square. Okay, and I have a function operand f of x is equal to cos x. F of x is equal to cos x. Again, let us write the operator equation. A of f of x is equal to 4x square into cos x. So we are simply multiplying this operator by this multiplication operator 4x square. So this is nothing but 4x square cos x, a new mathematical function which we will write it as g of x. So again, A of f of x yields a new function g of x. So this is one of the important class of operators called as multiplication operator. Now we will discuss about some important algebraic properties of operators, or about the algebra of operators. Okay, as I already told you, if the operator is written alone without an operand, it does not carry any physical meaning. It does not do anything. Okay, it has no meaning. But still, even though operator itself by itself does not have any physical meaning, it can still be added, subtracted, multiplied, or can obey different algebraic rules. Okay, just like numbers. For example, you can add two numbers, you can subtract two numbers, you can multiply two numbers, and you have different algebraic rule for numbers. So similarly, you can have different algebraic rules followed by operators, though they do not carry any physical sense or meaning if written alone. So what are the different algebraic properties of operators? The first property of operators is the addition of operators. So if we have more than one operator, okay, say for example operator A and B, okay, how do you add these two operators? So addition of operators. Okay, so what is this addition rule of operators? Tell. Suppose we have two operators. Okay, I will represent it by different symbol, operator A cap and operator B cap. Okay, I will remove that cap. I will only say operator A and operator B. And if I have a operand f of x, okay, I have a single function, an operand f of x, on which you can either apply A or operator B. Now suppose if I add the two operators and then apply it on the operand, that is A plus B. I am adding the two operators first, and the resultant operator I am applying it on the function f of x. This would give the same result if I had applied the operators individually on the function f of x and then added. Okay, so it would be giving the same result if I had applied operator a on f of x and operator b on f of x and then added those results. Okay, this property of operator is nothing but called as additional rule or additional property of operator. So either I can add the operators first and then apply it on the function, or I may apply the operators individually on the function first and later add them. Both give the same result. This property is the addition property of operators. Suppose if I have three operators, okay, then how will you write this addition rule of addition? First I will add the three operators and then apply them on a function, and on the other hand I will apply these individual operators and add them. Okay, I will apply the individual operators on the function first and then add them. Both give the same result. So it does not, okay, it is not important that whether you add the operators and then apply it on the function, or whether you first apply the individual operators on the function and then add them. Both give the same result. So this property of operator is called as addition rule or addition property. Okay, and by taking one simple example you can understand the addition property of operator. Okay, suppose one operator is, okay, d by dx. Operator A is d by dx. Operator B is d square by dx square, and the function f of x is cos x. Or okay, I will not take this function cos x, because when you apply both the operators and add them it will become 0. So I will take the example of 4x cube. Okay, suppose if I had applied individually a of f of x, okay, plus b of f of x, that is the RHS of this equation, what would be the result? D by dx of 4x cube plus d square by dx square of 4x cube. Differentiation is 12x square plus, first differentiation of 4x cube is 12x square. If again I differentiate it, it becomes 24x. On the other hand, if I add a plus b of f of x, on the other hand, if I add the two operators and then apply it on the function, it would be d by dx plus d square by dx square of 4x cube. And you know the property of differentiation, this can be written as d by dx of 4x cube plus d square by dx square of 4x cube. If you apply this differentiation, it turns out to be 12x square plus 24x. It is nothing but the above outcome, same as the above outcome. So this example, okay, clearly suggests the rule of addition. The second important algebraic rule or the property of operator is subtraction of two operators. the subtraction rule is very much similar to the rule of addition. If I have two operators a and b and a function f of x, okay, if I first subtract the two operators a minus b and then apply it on the function f of x, it would give the same result if I had applied a on f of x and b on f of x. Find out the result and subtract one from the other. Okay, so a minus b of f of x is equal to a minus f of x minus b of f of x. Sorry, a of f of x minus b of f of x. So this rule mathematically is very much similar to the rule of addition. The only difference is that instead of plus you have minus here. On the other hand, what is b minus a of f of x? Okay, remember, when you are adding numbers or operator, the sequence or the order in which you are adding will not be important. Example, 2 plus 5 and 5 plus 2, okay, both give same result. But in subtraction, the rule, how you are applying the order of writing the numbers or the sequence of writing the numbers is very important. For example, 2 minus 5 and 5 minus 2, where I have interchanged the two numbers, they don't give the same result. So here also operator a minus b and operator b minus a may not give the same result. So the sequence is very important. So b minus a of f of x will be b of f of x minus a of f of x. Okay, so in general, okay, if I write the addition and subtraction rule together, you can write a plus or minus b of f of x is equal to a of f of x plus or minus b of f of x. Okay, so this equation or rule is applicable or represents both addition property as well as subtraction property of operators. Okay, for example, if I have a minus b plus c of f of x, where you have both addition of operator as well as subtraction of operators, in such case you can write, okay, based on your definition of addition and subtraction property or rule, you can write this as a of f of x minus b of f of x plus c of f of x, right? So this is the simple rule of addition and subtraction. The next important algebraic property of operator is the operators can even be multiplied, but how they are multiplied, okay, is somewhat different from multiplication of numbers. So let us understand this multiplication of operators. So if we have two operators, operator A and operator B, okay, two different types of operators applied on a function f of x, which is an operand, then what do you mean by operator A into operator B? Okay, so operator A into operator B is an operator, new operator. Okay, what do you mean by a into b of f of x? The meaning of this is that you are applying one operator on the function followed by another operator. That is called as multiplication of operator. So what do you mean by a into b of f of x? First you are applying one of the operators on the function followed by the second operator, but how in which sequence you have to apply, that you have to remember. See, remember the sequence of application is from right to left. So in this case, which is the operator in the rightmost corner? Operator B. So first you have to apply operator B on f of x and then apply operator A on f of x. So please remember the sequence of operation or application of operators. It is always from right to left. Okay, this sequence is very important, because if you interchange the sequence, if I apply A and then B, it may or may not give the same outcome. So the sequence of application is very important. So let us define A into B of f of x is nothing but A of B of f of x. So this is the multiplication of operator, definition of multiplication of two operators. First you are applying the operator B on the function f of x. It will give some function, new function g of x, and on this new function g of x you have to apply the second operator. So this would be A of, if I apply this operator B on f of x, it gives a new function g of x, and on this new function I am applying the second operator. When applied, it gives one more new function, that is h of x. Similarly, how will you define B into A into f of x? Remember again, the sequence of operation is from right to left. So first you have to apply now operator A followed by operator B. So this would be B of A of f of x, that is B of A of f of x gives a new function which I will take it as g dash of x, and when I apply this operator B on g dash of x, it yields another function h dash of x, and we do not know whether h of x and h dash of x are one and the same. If they are same, fine, the sequence of operation does not carry any meaning. Either you can apply operator A first or operator B first in such case. But if these two results are different, then remember the sequence in which the operators are applied becomes very important. And this multiplication of operator is not just restricted to two operators. You can even multiply any number of operators. Say for example, let us try to define the multiplication of three operators. What do you mean by operator A into B into C of f of x? Again, the sequence is very important from right to left. So what we are applying? First we are applying C, operator C on the function, and then we are applying on this the second operator B. Okay, whatever result you get on that, you are applying the second operator, you get one more result on which you are finally applying operator A. So A into B into C of f of x is A of B of C of f of x. First operator C is applied, and then operator B is applied, and finally operator A is applied. Let us take one example. Okay, example 1. Suppose operator A is d by dx, operator B is d square by dx square, and the function is sin x. Okay, let us first calculate A of A into B of f of x. What is A into B of f of x? It is A of B of f of x, that is d by dx of d square by dx square of sin x, which is d by dx of, okay, what is the double differentiation of sin x? First differentiation gives cos x, the second differentiation gives minus sin x, and the differentiation of minus sin x is minus cos x. Okay, now let us try to calculate what is b into a of f of x. So which operator is now applied first? Unlike the first example, here a is applied first. So this is b of a of f of x, that is d square by dx square of d by dx of sin x. What is d by dx of sin x? Cos x. So d square by dx square of cos x. If I take double differentiation of cos x, first differentiation would give minus sin x, and its differentiation again would give minus cos x. So this is the result of b of a of f of x. Okay, so we have multiplied two operators in two different sequences. Okay, in the first we calculated a into b, in second we calculated b into a. But in this particular case, the results given by both are one and the same. So for operators d by dx and d square by dx square, the sequence of their multiplication is not important. Either you can apply a first followed by b, or you can apply b first followed by a. But this is not true for all the cases. Let me give one more example. Say for example, operator a is now 4x square, a multiplication operator. Operator b is d by dx, and the function f of x is sin x. Okay, we'll stick on with the simple function. Now let us try to calculate a into b and b into a. What is a into b of f of x? It is a of b of f of x, that is 4x square into d by dx of sin x. First let us apply this. D by dx of sin x is cos x, the new function. On that we are applying the multiplication operator, so this becomes 4x square into cos x. On the other hand, let us try to calculate b into a. b into a of f of x is b of a of f of x, that is, what is b? D by dx, it is applied later, of 4x square into sin x. So here the multiplication operator is applied first, so it becomes 4x square sin x, a new function g of x, and on that new function we have to apply the second operator. So if I apply, it becomes 4x square into cos x plus 8x into sin x. Using the rule of differentiation, okay, you get this result. Now it is clear that a into b is not equal to b into a. So in this particular example, these two operators, okay, give different result for a into b and b into a, and therefore we should be very careful in knowing in which sequence we have to apply these two operators. So when we are working with the new operators, it is always to be very careful to know the sequence in which the operators has to be applied. Okay, I will stop here. In the next video I will discuss about some more property of operators, such as commutative property.